Hello, test, 1, 2. Hello, Crocus Plains High School, grade 9 math. This is unit 7, similarities and transformations. Of course, the first thing that I always want to do is help a kid to understand what's going to be in this unit and why they need it. So this unit is really made up of 3 parts. Each part leads to an understanding of the next part. No kidding. And together, the 3 parts form a basic understanding of proportional geometry and transitional geometry, all right? So those are 2 really important concepts. So here's part 1. Part 1 that we're going to learn about is about scale factor, and that's what this little movie's about, scale factor, and finding missing proportions of similar shapes. This is really useful in understanding maps and how very large things like blue whales and skyscrapers can be drawn accurately on a piece of paper. It's also the math that allows us to accurately draw a very small thing like a virus. Get lost, COVID-19. The scale factor stuff acts like a guide as to how a drawing or model relates to the actual object. Part 2, and that's going to be the second video, is all about symmetry. All the art kids really like this because they get to draw stuff. It's also cool that an understanding of symmetry leads us to an understanding of the beauty in nature and man-made objects. That's what's really cool. I mean, what's really cool about that is that the beauty lies in the math. And part 3 is all about rotational symmetry. This means that we can move a shape, like you may remember, flip, slide, and turn from grade 6, and express exactly where the object will end up on, yes, wait for it, gonna grab a highlighter, the coordinate plane. If you play first-person shooter games or any video games where an object moves, rotates, slides, then this is a very basic math of that game. Understanding rotational symmetry lends itself to a very basic understanding of computer coding. But how do we know all this stuff? What are we supposed to know already? Well, to be successful in this unit, we need to remember from previous math concepts an idea of a ratio. If we wanted to state the ratio of stars to hearts, like the little group I have here, we could write the ratio in 3 different ways. We could write it in a sentence. The ratio of stars to hearts is 6 to 4. So that's a sentence. Or we could write it like that, 6 dot dot 4. Or what even looks like a fraction, 6 over 4. Critically important to remember that we have to keep the numbers in the right order. If we mention stars first, then the first number has to be the number of stars. And also remember that every ratio can be written as a fraction where the first term is always the numerator. That's the top number. And the second term is the denominator. That's the bottom number. So if we wanted to state the ratio of, say, check marks to x's, we could write it as either 3 dot dot 6, 3 dot dot 6, or 3 over 6. It's important that when we say check marks as to x's, 3 is the number of check marks. If we said it's coming first, then we have to write it down first. And if it's first, it has to be the first one in the fraction, the numerator. The ratio, though, simply means that for every 3 check marks, we get 6 x's. Hope that's not a math test I wrote. So, just because I'm a math teacher, we notice that 3 over 6 can be reduced to half, which means for every 1 check mark, I get 2 x's. So if I had 15 check marks, I would expect, that's right, 30 x's. It's a ratio, and it tells me how things can change. And that's essentially how scale factors work. They tell us the way in which a ratio between an original object and its model or reproduction changes. Scale factors are multipliers. And with the help of amazing Dr. Zed, we can do a lot of cool math. Just remember, in this unit, the diagram is always mentioned first. And the actual thing is always mentioned second. Even if it's like a fraction, the number on top is diagram. It says that there. And the second one is the actual thing. That's important. The first number in the ratio is the diagram. The second number is the actual thing. Okay, well, let's see how this scale factor works out. A scale drawing is a drawing where the dimensions are proportional to the actual size of the object being drawn in a predetermined ratio. So here we have a snail guy, and it looks like the original. Let's say that this guy is the original one, and this kid wants to make a copy of it. And to do it, he drew it on a bigger grid. Well, that's not haphazard. See, the squares help us to tell or keep a guide as to how to draw it. And the scale is a ratio of the size of the drawing to the size of the original object. And this is referred to as a scale factor. So for example, if the scale is 1 to 3, then the length of 1 centimeter in the drawing represents 3 centimeters in the original size. Oh, okay. So basically, every 1 centimeter in the drawing stands for 3 centimeters in the actual. Here's for all the formula kids, and they're looking for a formula. Here's how we determine scale factor. Scale factor is the length on the drawing or map divided by the length on the original. I like to call it LOD, length on drawing, over LU, length on original. LOD over LU, LOD over LU. Just a neat way to remember it. Diagram over original. Well, let's have a look here. Here I have a tow truck, and over here I have a model of a tow truck, okay? So let's find out the scale factor of this tow truck. Here it says the actual length, LOD over LU, so length on diagram. Well, that's over here, 0.25, so I have 0.25 divided by length on original. Oh, so actual means the original, 9.5 meters. 9.5 meters. Now, it's important to know they're both in meters, so we're not going to get hung up on that, okay? So I go in there, grab my calculator, and I go 0.25 divided by 9.5, I get 0.0263. That's the scale factor. But what does it mean? The scale factor tells us the proportion of the sizes between the two tow trucks. The length of the model is 0.0263 of the actual length of the tow truck. So let's say I've got this model right here, and my friend says, hey, how big is that? Well, I could say it's 0.0263 of the real thing, which means it's kind of small compared to the real thing, but it is a model. Okay, so what? Well, the really cool thing about this scale factor is that all of the measurements on the model will be exactly 0.0263 of the original truck. This means that if the front grille of the real tow truck measured 3.2, then all we would have to do to build the model to scale would be to multiply by that number. And we get 0.0842 meters, which is really 8.42 meters because there are 100 centimeters in a meter. Cool. But what if we knew the height of our model truck and wanted to find the height of the real truck? Could we do that? So let's say we know that this is 0.12 meters, which is 12 centimeters, and we want to know, well, how much is the real one? Could scale factor help us? I mean, if scale factor can help us go from big to little, like making a model, can it go from little, which is the model, to big, which is the actual thing? And that's a really nice thing about scale factor, is it's a ratio. You bet. So let's say the height of the model truck is 0.12 meters. All we have to do is set up Amazing Dr. Z and do the math. Now, if you don't remember what Amazing Dr. Z is, let me help you out. Okay? Amazing Dr. Z. So we set up our formula, which is scale factor is log over Lu, and we can always put scale factor over 1 because we can. Any number can be written over 1 unless it's a really stupid repeating decimal. Okay? Now, remember, Amazing Dr. Z always starts from the thing you want to find out. We want to find out the length on our original. We'll call that X. And from the X, we draw a Z. Zip, zip, zip. And remember, Amazing Dr. Z is always equal to the one across if you multiply the corners and divide by the last term. Okay, so I'm going to have 1 times 0.12, which is 0.12, and I'm going to divide it by my scale factor, which is 0.0263. I'm just setting up an Amazing Dr. Z, and I get 4.56 meters. So the nice thing is I can go from a big thing, use a scale factor, and to make a little bitty thing. Or I can go this way, or I can go this way and make it big again. And scale factor will tell me how to do it so that every part of it is right. That's pretty cool. That would be important if you're in engineering or architecture, or if you're modeling stuff, that's how it goes. Okay, let's do some examples just to make sure we got it solid. Okay, so here's some examples. We want to determine each scale factor. Here I got a toy, which is my diagram, and I've got a giraffe, which is actual. Now that 6,100 centimeters for the giraffe is actually how many centimeters tall a giraffe is. Most giraffes are about 6.1 meters tall, and there's 100 centimeters and yada, yada, yada. Anyway, you get it. So I'm using actual numbers. So length on diagram, I'm going to have 750 divided by my actual, which was 6,100. Grab my calculator. And there's my scale factor, 0.123. Now, that would mean, let's say I wanted to know about maybe how wide a giraffe is. I could use this scale factor to find out how wide the real one is, right? Or go from the real one to the little guy. That's cool. Okay, here's everybody's favorite insect of the summer. My wife loves these guys. Sarcasm. A wood tick. Okay, now here we've got a little guy. Its actual length is 0.25 of an inch, so that's 1/4 of an inch. And here's a drawing of 8.5 inches. So we want to know the scale factor. Here, if you check out the graph again, that number is less than 1. It's less than 1. It's not even 0, like it's less than 1. Well, let's see what's happening here. So to lengthen our diagram, we're going to go 8.5 divided by our original 0.25. See, I'm just filling this stuff in. Grab my calculator, 8.5 divided by 0.25. That doesn't look like a 2.5. There, now it does. And I get 34. Check that out. That's a big number. That's a lot bigger than 1. In fact, it's 34 times bigger than 1. I think we're going to be able to come up with some kind of a rule soon. Okay, anyway, let's look at this. So this kid has got a drawing of the Eiffel Tower. I think it's pretty good. And the actual Eiffel Tower. Now, just so that you guys know, it's not always easy peasy, lemon squeezy. Watch this. This is in centimeters. This one is in meters. You have to compare the same things. All right. So you could convert centimeters into meters or meters into centimeters. It really doesn't matter. I'm going to convert 15 centimeters into meters. So I'm going to divide it by 100 because I know there's 100 centimeters in a meter. Okay. Or I could add 2 zeros onto 324 meters. Maybe that's what I'll do. That might be easier. Okay. So my length on diagram, that's the drawing. So I've got 15. And I'm divided by length on my original. So I'm going to times this by 100. And I'll get 3,200. Oops, let me just erase that. Oops, no, there. Okay, back to here. Good. So I'm going to take 324 times it by 100, and I'm going to get 32400. That's 32,400 centimeters. Okay. So grab my calculator. And I go 15 divided by 32,400, and I get, whoops, 0.0463. Now, I would have gotten that if I had gone 0.15 divided by 324. So either way, I would have been good. Now, if you look at that, here we've got a big item, the Eiffel Tower, and we've got a drawing. And when the reproduction is smaller, we get a decimal. Like here we've got a big giraffe. And here, the reproduction is smaller, so we get a decimal. Let's change colors. Here, we've got a small thing, and the reproduction is bigger. We get a bigger number, a whole number. Okay, let's keep that in mind a little further down. But remember, all you need to know is Lod over Lu, and that's the scale factor. Okay, now we can use a scale factor to find a missing dimension. Okay, so here it says, use a scale factor to find the missing dimension. I think I just heard that. Okay, so here's the Statue of Liberty. Its actual height is 93 meters. And it says the scale factor is 0.0005. What's the height of the cartoon? Well, we just set up scale factor over 1. So that's going to be 0.0005 over 1. and it's going to be equal to log over Lu. So diagram is what we want to find out. So we don't know that. We'll just call it X. And Lu is the actual is 93 meters. Okay, what do we do now? Somebody say, amazing Dr. Z. Amazing Dr. Z. Okay, let's do that. Zip, zip, zip. So amazing Dr. Z is equal to the one across. If you multiply the corner, so we'll go 0.0005 times 93. We're going to take all of that and divide it by 1. And we get, well, I'm going to grab my calculator. 0.0005 times 93. The height of the drawing is 0.465 meters, which turns out to be 4.65 centimeters because there are 100 centimeters in a meter. Okay, here's another one. So let's look at this race car. Pretty cool, I think. Now, what we want to do, the model race car is 11.5 long. Now, a model is like a diagram. Model is like a diagram. So this is the real. So this is the original. And the question says, how long is the real race car if the scale factor is 25? Well, you're probably already thinking, well, if it's 25 times bigger. Yes, it is. So let's do that. So we're going to go 25 over 1. So we're just writing scale factor over 1 is equal to log over Lu. So my diagram is 11.5. And my original, well, we don't know what that is. So we'll just put an X. So just remember, amazing Dr. Z. Start from the X. Zip, zip, zip. So we're going to have X is equal to 1 times 11.5. And then we're going to divide. We're going to take that and we're going to divide by 25. Okay. Put everything in my calculator. So the actual length of the race car is 287.5 centimeters, which is 2.87 meters. Not bad. Not bad at all. So just to recap a little bit, we can find scale factor really easy by going diagram divided by original. And then we can use scale factor and amazing Dr. Z to find a missing part. That's pretty cool. Okay, so I will stick with a pen. So if a scale factor is greater than 1, this means that we have made, pick one, ready? A reduction, enlargement, or duplicate. Well, if it's greater than 1, we've made it bigger. So it's an enlargement. If the scale factor is equal to 1, then we've made an exact, pick one, duplicate. A duplicate is a thing that's exactly like the other one, like a Xerox copy. And if a scale factor is less than 1, we have made a reduction. Scale factors are the way in which the proportions change from the actual object to the reproduction. So scale factor is a multiplier of the original dimension. But, I spelled that one too, please. How come on a map a scale is written like this? Like here for New York City. And it's got a couple of things. It says 1 inch is equal to 1 mile, 1 dot 63 1,360, and then this little scale thing in the bottom. Well, let's break it down. This first part, it's the ratio. This tells us that for every 1 inch on the map, it represents 63,360 inches, or 1 mile of length in New York City. So 1 inch to 1 mile, those are different units, and that's kind of not cool. So what we really have to say is a mile is really 63,360 inches, because it is. They put 1 inch as 1 mile just to make it easy for tourists who might get lost. So when a scale is written in this way, the first term is usually 1. So that might be 1 inch, 1 meter, 1 mile, 1 kilometer, whatever. And the second term is how many units are actually there. So it's still scale. Now this little bar thing here is basically if you wanted to take your, say, your thumb and put it over that and then put it on the map, you could count that many miles. It's for real intrepid travelers. So if I measured 3.5 on the map, 3.5 inches on the map, I could use scale to find out the actual distance like this. So remember, the first number is always on the diagram. 1 inch on the map is 1 mile actual. So 3.5 miles on the map, well, look, folks, all I got to do, amazing Dr. Z, zip, zip, zip. So that's going to be x is equal to 3.5 times 1 divided by 1. So if I measured 3.5 inches on the map, I'm really going 3.5 miles. So, okay, where are Lod and Lu? Remember, the first number is always Lod, and the second number is always Lu. Okay? So the diagram is always expressed first in the ratio. The actual is always second. So scale factor can be written in several different ways, but they all mean the same thing. So let's use this example. Here's a cool circle, and it's got 1, 2, 3, 4. And this one has only got 1, okay? Now, well, that almost looks like a Pac-Man. Anyway, so let's use this example. The large circle has a radius of 4 squares. The smaller square has a radius of 1 square. So we can say that this drawing has a ratio of Lod to Lu of 1 to 4. That means from the reproduction to the original. Because remember, the first number is always the diagram. Okay? Or we could say Lod over Lu like a fraction, 1 over 4. Now, we could take that 1 over 4 and you could turn that into a fraction, or I mean a decimal, 0.24, or keep it as a fraction. That's okay too. It's fine. Now, okay, and the very cool thing that we can do, even if a scale is written like it is on the map, is to set up an amazing Dr. Z, and we can find out any part that's missing. Okay, so let's say, for example, just for giggles, let's say our scale factor is equal to 1 over 4, just like that, okay? Then let's say our reproduction, our repo, let's say our reproduction circle has a radius of, let's say, 16 squares. Now that doesn't even look like squares, but it says squares, okay? Believe me. Okay, so what do we do? Now, this is kind of different because what we're trying to do is use a fraction as a scale scale factor, but can we still do it? Absolutely, because we can still write it as an amazing Dr. Z. Check this out. So 1 over 4 is our scale factor, is equal to log over Lu. So length on diagram, that's our repo, is 16 over Lu, our original. We'll just call that X. See, we can set up an amazing Dr. Z because if scale factor is a fraction, we just write it like a fraction and then set up log over Lu. And what do we do next, kids? That's right. Zip, zip, zip. Okay, so we're going to say X is equal to 4 times 16 divided by 1. Well, okay, so 4 times 16, so 6 times 4 is 24, 4 carry the 2, 4, so that'll be 64 over 1. Our original will have 64, a radius of 64 squares. Man, that's pretty good. All right. Okay, now that brings us to the end of scale factor. Now, without getting you all bored and stuff like that, basically, scale factor is a ratio, and it tells us how things change from getting bigger to getting smaller. And as it changes, every part of it changes in the same way. And then what we're going to do is we're going to get into this thing about symmetry, and we're going to get into proportions, so that if one thing changes, it changes in a beautiful way. And then we'll maybe get into rotating some stuff and working on that coordinate plane, which you know so well, so you can actually be able to plot where things move. So if you're to go into computer science, then you got this knowledge. All right. So I'd like you to do the assignment. It's called scale factor assignment. It's in Teams, and the answer key is attached to it, so you can see how you're doing, and that way you can get back to me and say, hey, Mr. Chambers, I am absolutely knocking this out of the park. Or, hey, Mr. Chambers, my mom can't figure it out. Can you help me? And we can set up a video chat. All right? Hang in there, guys. Stay safe. Stay isolated. Stay at home.